Hello everyone, this is Kadir here, and in the last video we talked about part 1 of the vision sensor tutorial and how we can use the vision sensor and the logic behind tracking an object in a single dimension. And we watched this video which this person's moving this yellow goal in one dimension, and this is actually from a previous year, so the game elements are a little bit different, but he's moving it in one dimension and the robot is successfully turning to track that object. Okay, so we talked about the use of a single motor to move back and forth, but technically, if you put positive power to one side of the robot and negative power to one side of the robot, it's gonna start turning. So what you're doing is just multiplying the value you get from that equation by -1 and plugging it into the other side so it tracks perfectly. So again, he's moving this in one dimension, the robot is turning in one dimension to track that goal. So before we actually dive into the code of implementing this to track our spin-up goals like so. So here, yeah, you can see the robot's not even aligned, and as soon as I press a button, it's going to align itself. And this is actually working in 2 dimensions, because if you notice, the robot moved forward to get to the right distance, and it also turned to align itself properly. So if you notice here, again, it's not aligned at all, and you saw how the robot turned and also moved. We're going to look at how we can achieve that. So a critical thing to understand about cameras is that they can't tell you how far away you are from an object, but they can give you the size of it. If you notice in the VEX Code software, one of the sensor values we can get for the object is its width and height. And assuming our goal looks something like this, right? I'm just drawing a box here. We know this value, and we also know this value right here. When we multiply this together, we actually get the area of how much the camera sees. The closer we are to this value, the closer the object, or the closer we are to, the bigger the value is, the closer the camera is to the object, right? And the smaller the value is, the further away from the object it is. Using that information, we can actually have a second dimension of control. What we can do is we can use the same logic from the crosshair logic from last time we discussed, where if the goal is right here, we just apply like an increasing or decreasing power using a proportional control algorithm to center the goal, right? But we can also use the size of the object to move the entire camera back and forth. And this is how we are able to actually do this. We're using the size of the goal in the camera, and we're moving the robot so it's just the perfect distance away. And we're also turning the robot so it aligns with the goal. So how am I doing all these things at once? And if you look at the code, it doesn't even look like there are that many lines of code to begin with. So how is this all happening in these few math blocks? Let's take a look. So the easiest way to get an understanding of like power and power distribution on a robot is through the use of vectors. So I'm just going to use arrows and add up those arrows to find out where my robot's going. Okay, so let's say like in a map. Okay, so let's say that's this entire white screen is our field. I have a goal right here, and I'm gonna draw the target position of my robot to be right here. Okay, so anywhere in this range we're fine. So what I'm gonna do is look at the camera. So the camera's field of view is, I'm gonna draw it in green. So let's say the robot sees this much on one side and this much on the other side. Okay, so the field of view, the goal is inside the field of view. and we know the distance from the center. And so at the very beginning, in that while loop, so at the very beginning we have a distance from the center value to turn. So let's think about this for a second. To turn our robot, we need negative power on the left side and positive power on the right side. So these two arrows represent the power. Okay? And let's look at the second dimension. Okay? So the second dimension is actually the distance. So as far as the robot is concerned, this object is way too small. It needs to go closer to it. Okay? And to go closer to it, we have power on both sides. So we have two arrows facing the forward direction. Now, this might look like it's not going to work, but if you think about it, if you add up these arrows, you get one really big arrow on one side and one slightly smaller arrow on the other side. So now, because you have a difference in power, the robot is actually going to start turning this direction. Alright, so the robot's moving forward and also turning at the same time. So I'm going to erase that field of view, and actually the robot itself. And I'm going to draw the second time it loops around. So now that a robot has started turning, let's say it's facing like this direction. Okay, it's closer to the goal. And now if you look at the snapshot, let me switch back to green. Okay, let's pretend like that's the field of view. It's much closer to the center, right? So let's do the arrow method again. So now you have power a little bit on this side, little bit on this side, because it still wants to turn, but we still think the object is too small. So we're going to do a lot of power on this side and a lot of power on this side. Alright, and now if you think about it, we have more power here and then little less power. So again, it's going to continue going in that path, it's going to continue turning, and eventually when this is centered on the line, what's going to happen is you're not going to have these arrows anymore because it's going to be 0. And you'll only have the forward arrows, which means that your robot will only go forward. So let's look at this again and try and visualize our vectors, okay? So hang on one second. I'm going to find the point in the video where the robot goes right here. And okay, I'm going to screenshot this. And let's draw the vectors out. Alright, so here in this screenshot, our vision sensor is facing this direction. Actually, let me make the pen a little bit bigger. So our vision sensor is facing right here, and let's say our field of view is more than big enough, okay? So we know this distance. It's going to be some pixel value. And we're going to put that through a function, and we're going to get a power for the motor. That's going to give us a negative value on the left side and a positive value on the right side, right? And now we look at the area of this goal right here. What do we see? Let's say this is, realistically, I would say this would be around like 1000 pixels. Let's say it's 50 pixels wide by 20 pixels tall, okay? So now, because it's still really small for our robot, it needs to go closer. We'll put some power here and some power here. And we're just adding these two arrows, and that's what the robot's doing multiple times a second. Just checking where it is and adding arrows. And this is actually a feedback loop. This algorithm we're using relies on sensor information to correct itself. So if it's far away from a target, it'll increase its speed. And if it's close to a target, it'll decrease its speed to be precise. And that's the way we're actually getting it to work. So if you run this through multiple iterations, so now let me erase this for 1 second. So let's say this distance is like 50 pixels for now. The next second is going to be 45. We're changing the power of the motor. The next second is going to be 30. Next second is going to be 20. and the next second it's going to be 10, and eventually it'll be 0. That is in theory, okay? So the logic is almost there. We're just missing one small step of the problem, and that is that robots are not perfect in real life. In theory, the logic will work, but this logic will not work in practice. Let me tell you why. Okay, so what's going to happen is your robot will never be able to get exactly to that 0 and hold its position, because there's always like these microscopic movements going on in your motors that just slightly throw it off overboard, or sometimes even throw it a lot overboard, and it starts correcting itself like multiple times a second, and it's going to go into that loop. We don't want that to happen. So what we're going to do is actually program what's called a dead zone, meaning that we're essentially, instead of our target being a point, it's like a small circle. And as long as it's within that circle, somewhere within that circle, a reasonable dead zone. Let's say, like for example, if this green dot, let me not use green because there's a lot of green dots. Let's say this light blue dot is our target. Our like actual, I guess like camera is fine as long as it's like within this square. And that dead zone is what is going to tie all our code together and make it work. So let's look at the code itself and see if we can break this down, okay? So first I have an else if statement, or an if statement, which is just there to stop the motors if the object doesn't exist. This much is pretty simple. And then next up, I have an if statement, and this is our dead zone, okay? So if the center x minus 160 is less than 20, and this is the absolute value, right? So what I'm doing is just checking if there's a 40 pixel dead zone in the x direction, all right? And again, the 160 value I got from the VEX website for the documentation for the camera. It's the same on every camera, but our values are a little bit different because we messed around with it and found out what works best for us. Okay, so we have a 40 pixel dead zone in the x direction and a 200 square pixel dead zone for our area itself. So here we're comparing the distance alone, giving it a dead zone, and here we're actually comparing the area and giving it a dead zone. So we're taking the absolute value of the width times height, and minus 2800, that is our target area, okay? So our original area minus our target area will give you essentially the remaining, and if the remaining is less than 200, that's okay. The robot is just supposed to stop, okay? It's going to stop. That's our dead zone. So what we're doing is we're drawing like a virtual boundary around our goals, around our spin-up goals, so that as long as the robot is within like this % range of error, you're fine. Like it'll still work. And in the else part is where we have our actual rest of the code. So here, I'm just going to take one of these parts out. The other one is just the opposite, or actually it's the same for the area part, but it's the opposite for the turn. Okay, so actually let's pull them both side by side and compare them. So our first part is gonna be our main move forward block. So this controls how far away from the goal our robot is going to be, right? So yeah, 2800 is our target value. That's what we want the area to be. And again, you can find all this information through the vision sensor calibration tutorial, which will be uploaded soon. Okay, anyways, we're getting the area of the object that the vision sensor sees, and we're comparing it to the target area, right? And we're multiplying that with a multiple of a coefficient of 0.04. And that is actually going to be the power for our motor, part of it at least. And on the other side, we're doing our logic with the center This tells you exactly the heading of the robot and how far away from the like center of the goal the robot is, right? Like the turning part of the robot. So we have our two big vectors, which is this, which is the same in both sides as you can see. And then we have our two opposite vectors, which is center x minus 160 times 0.2, center x minus 160 times negative 0.2, which is going to be added. So these two things added is going to give you the power for your motor. So I hope that helped. Again, it's called a proportional control algorithm, and what we're doing is we're just comparing um, the what the camera is seeing to what we want to see multiple times a second, and we're adjusting our power values and speed values accordingly. And in the end, you get a beautiful result like so. So yeah, so you can see how it's like correcting itself. It's literally the coolest thing ever. Actually, let me slow this down for a little bit. So you see how it overshoots a little bit and then turns back to correct itself? Yeah, that's the power of PID. Thanks for watching. I'll see you guys again in another tutorial.